Now, this bit for straight lines, what I want to give to you is just another tool in kinematics that we are going to use all along. So you might just open your physics notebook. Although it does not matter, you can use your maths notebook also. Now, when we started calculus, and I told you y is a function of x, when I said y is a function of x, then ddx of y or dy dx meant rate of change or instantaneous rate of change of y with respect to x at x, right? This was the algebraic understanding of this notation. dy dx, instantaneous rate of change of y with respect to x. And the computation of this was obtained by taking limit delta y by delta x, change in y divided by change in x, as that change in x came closer and closer and closer to 0, right? That's how we computed rate of change of y with respect to x at x. Limit delta y by delta x, as delta x was brought closer and closer and closer to. Now, let me give you a geometric understanding of the same, which is extremely important. Now, when I say y a function of x, for example, is 2x plus 1, right? Then in the xy plane, this x and y variation, y is a function of x, which is like 2x plus 1. This x and y variation is represented along a straight line. Do you realize that y equal to 2x plus 1 is a straight line? Like this, with slope m equal to 2, with y-intercept 1. It becomes 0 at x equal to minus half, right? So for any given x, this was y, which was a function of x. Function of x means a certain rule applied on x to give me y. What was the rule applied on x? The rule applied was 2x plus 1. Twice this plus 1 gave me this y. Y equal to a function of x, that was 2x plus 1, right? So at x equal to 1, the value of y was 3. At x equal to 3, the y was 6 plus 1, 7. So for different values of x, you got different values of y, which was a function of x. So this was the graph of y versus x. This was the plot of y, which is a function of x versus x. Y versus x. This was the plot of y versus x. Variation of y with x. This was the variation of y with x. Clear? Suppose you had y, a function of x, going as x squared, for example. Y, a function of x, going as x squared, for example. So at x equal to 0, y is 0. right? So this is a point 0, 0 on the graph of the function, right? When x is 0, y is 0. If y is x squared, right? X equal to 1, for example, y is 1. So 1 comma 1 is a point on the graph of the function y is 1 squared, right? At x equal to 2, y is 4, and so on and so forth. That means x is 2, y is 4, and so on and so forth, right? So this way, you take various values of x and you plot the corresponding values of y to get points x comma y. For a given x, y would be x squared. For a given x, y would be x squared. So all sets of x and y going as per y equal to x squared are plotted, right? And then when you do that plotting, that y a function of x, that is x squared, will look like this, So at x equal to x1, y would be y1, which is f of x1. And how is it obtained? The corresponding y for x is obtained as square of x. So will be x1 square. For a given x, the y is obtained as a function of x. The y would be x square. For a given x, the corresponding y would be square of the corresponding x. And so you get a set of points x comma y commensurate with y equal to x squared. You get a set of points x comma y commensurate with x squared, and you connect all those points as in a graph. That will give you the graph of y equal to x squared, right? Fair enough? Now, so suppose the graph of a certain function of x, was this. Graph of a certain function of x was this, for example, right? For a given x, this was y. For another x, this was the new y, and so on and so forth. Y, so for a given x, this y would be dependent on x, would be a function of x. A certain rule would have to be applied on x to get the corresponding value of y. That rule could be, let's say, x squared, or that rule could be 2x plus 1, or that rule could be sine x, or that rule could be x cubed plus x squared to get the corresponding value of y, right? It will depend on the value of x. So you connect all those points and you get the plot of y a function of x, Okay. Now, having done so, let me select 2 points on the graph of the function, a point P and a point Q. Let me select 2 points on the graph of the function, a point P and a point Q. If I join P and Q, what I get is a secant to the curve, right? This is a secant to the curve. Yes or no? The secant to the curve. If I join P and Q, then the line obtained is a secant to the graph of the function, Now, suppose the tangent drawn at P. Suppose P is a fixed point. Suppose P is a fixed point, right? Then you can imagine a tangent at P. This is a tangent at P. This is the tangent at P, right? Now, let Q be a moving point. Let Q be a moving point. Right. If Q is a moving point, PQ would be a variable second. P is fixed, but Q is moving. So the second PQ would be a variable second, right? So causing this second to be variable. Now if P is fixed and Q is moving, the second is as if it's hinged at P. The second is as if it's hinged at P, right? So the second rotates about P. The second rotates about, right? Now, let me bring Q closer and closer to P. Let me bring Q closer and closer to P. All right. Say Q is brought to a position Q prime. Q is brought to a position Q prime, right? Then the second will become PQ prime. The second will become PQ prime. Bring Q even closer. Bring Q to Q double prime. Bring Q to Q double prime, right? Then look at the second. This becomes the new second. Right? This becomes a new second, PQ double prime. Bring Q even further closer. Then you get yet another second. You get yet another second. Q triple prime, PQ triple prime, and so on and so forth. Right? Now, do you realize that eventually, as Q is brought closer and closer and closer to P, all the seconds are rotating about P, hinged at P. All the seconds are rotating about. But there is a limiting position of the seconds. The limiting position of the second, no matter how close Q gets to P, no matter how close Q gets to P, the limiting position of the second will be the tangent at P. Can you visualize that? The limiting position of the second will be the tangent at P. Yes or no? Right? As Q comes closer and closer to P, the limiting position of the second of the seconds is the tangent at P. Right? When Q is brought closer and closer and closer and closer to P, then the second PQ comes closer and closer and closer to the tangent at P. This is what it means, right? The second PQ comes closer and closer and closer to the tangent at P. Second PQ comes closer and closer to the tangent at P. Does it make sense? Huh? Now, having said this, can I wipe this off? say there is a point P whose coordinates are x coordinate is x and y coordinate is a function of x. Y coordinate would be a function of x. It could be 2x plus 1, it could be x squared, it could be x cubed. So its y coordinate is f of x. A certain rule is applied on x to get the corresponding y for x, right? This is x and the y here is f of x. The y here is a function of x. Clear? Think of the point Q, which has its x coordinate as x plus delta x. Its x coordinate, let's say, is x plus delta x, where this length is delta x. This length is delta x, right? If this is x plus delta x, that means this length must be delta x, change in x, final x minus initial x, right? That's change in x. So x coordinate of Q is x plus delta x. Again, to get the y coordinate, you will have to apply the rule f on x plus delta x. So the y coordinate would be the value of the function at x equal to x plus delta x. That would be the y coordinate of the point Q. Clear? Now, between P and Q, so this length is y equal to f of x plus delta x, right? Whereas the length qm is going to be f of x plus delta x. This is f of x plus delta x and this is the same as this. If this is fx, this is fx and this is f of x plus delta x. So what is qm? F of x plus delta x minus fx. Qm is f of x plus delta x minus f of x. Right? This is the second, and the second makes an angle phi with the positive direction of the x-axis. The second makes an angle phi with the positive direction of the x-axis as shown. This is the second, produce it to meet the x-axis and it makes an angle phi with the positive direction of the x-axis. So what is this angle? Phi, right? Tan phi then is this, which is change in y. This is change in y divided by this, which is change in x. Change in y divided by change in x. That means the slope of the second, this is m, slope of the second is tan phi, which is change in y divided by change in x. Change in y divided by change in x. Hey, but change in y divided by change in x is what? An average rate of change of y with respect to x. When you go from P to Q, y has changed and x has changed. But the average rate of change of y with respect to x in the interval x to x plus delta x is what? Is the slope of the second. Slope of the second is in the interval delta x to x plus delta x. Average rate of change of y with respect to x is the slope of the second. Slope of the second between P and Q. Clear? Now, having understood this, slope of the second is always the average rate of change of y with respect to x in the interval over which the second is drawn, x to x plus delta x. That's the interval over which the second is drawn. P x comma fx and Q whose x coordinate is x plus delta x and whose y coordinate is f of x plus x, right? That's Q. This angle is phi. This angle is phi. Now, this is the tangent drawn at P. This is the tangent drawn at P. Tangent drawn at P. And the tangent makes an angle theta with the positive direction of the x-axis. That means slope of the tangent is tan theta. This is the tangent at. Slope of the tangent is tan theta. Clear? Now, this, like I said, is x. This is x plus delta x. And this is delta x. This is delta x. As Q comes closer and closer to P, first of all, what is tan phi? Slope of the secant? Slope of the secant, which I said was like change in y divided by change in x between P and Q. Change in y divided by change in x between P and Q. Slope of the secant, which also is the average rate of change of y with respect to x over the interval x to x plus delta x, right? So, tan phi is delta y by delta x. Now, as Q comes closer and closer and closer to P, as Q comes closer and closer and closer to P, means like this. Realize that Q is coming closer and closer and closer to P. What is happening to delta x? Delta x tends to 0, it shrinks, right? Delta x tends to 0. As Q is coming closer and closer to P, delta x tends to 0. And the secant comes closer and closer and closer to the tangent. The secant comes closer and closer to the tangent in the process. That means, if the secant comes closer and closer to the tangent, that means the secant is beginning to align itself along the tangent. That means the secant is gradually beginning to align itself along the tangent. That means the angle phi comes closer and closer and closer to the angle theta. That means the angle phi comes closer and closer to the angle theta. Yes or no? Right? Phi comes closer and closer to theta. Where theta is what? Theta is such that tan theta is the slope of the tangent at. Clear? That means tan phi is coming closer and closer to tan theta. Right? That means delta y by delta x. Tan phi is delta y by delta x. If Q is here, P is here, tan phi is delta y by delta x. We've seen that, right? That means delta y by delta x comes closer and closer to tan theta. Delta y by delta x comes closer and closer to tan theta. Yes or no? Now, what is happening? Take this statement as delta x tends to 0. Delta y by delta x comes closer and closer to tan theta, which is the slope of the tangent at P, which is the slope of the tangent to P. So then, consolidating both these statements, that is, as delta x tends to 0, as delta x tends to 0, delta y by delta x tends to tan theta. Delta y by delta x tends to tan theta. Putting them together, I say limit of delta y by delta x, limit of delta y by delta x as delta x tends to 0, limit of delta y by delta x as delta x tends to 0 is tan theta. It simply means that as delta x tends to 0, delta y by delta x tends to tan theta, which is written as limit of delta y by delta x as delta x tends to 0 as tan theta. Hey, go back to first principles. Limit delta y by delta x as delta x tends to 0 is dy dx. Is dy dx is instantaneous rate of change of y with respect to x at x, right? So this is dy dx at x. This is dy dx at x. Right? And what turns out then is that the rate of change of y with respect to x, that is the instantaneous rate of change of y with respect to x, is the slope of the tangent at x. This is slope of the tangent at x, yes or no? This is the slope of the tangent at x. The instantaneous rate of change of y with respect to x is the slope of the tangent at x. That means at any given x, you locate the corresponding point on the graph of the function, draw the tangent at that point, find the slope of the tangent tan theta, then this tan theta will give you instantaneous rate of change of y with respect to x at x. At any given point, you draw the tangent at that point, compute the slope of the tangent at that point, then the slope of the tangent at that point will give you the instantaneous rate of change of y with respect to x for that x. Got me? So that's the geometric interpretation of dy dx. If you draw the graph of y equal to fx versus x, then to find the instantaneous rate of change of y with respect to x, that is dy dx, all that you need to do is construct the tangent at that point, compute the slope of the tangent at that point. The slope of the tangent would reveal the instantaneous rate of change of y with respect to x. Make sense to you so far? No confusion at all? Okay. So then, suppose this is the graph of the function. At this x, the instantaneous rate of change of y with respect to x will be given by, at p for example, which corresponds to a certain x. The instantaneous rate of change of y with respect to x will be given by, suppose this is a line parallel to the x-axis, will be given by tan theta 1, right? Instantaneous rate of change of y with respect to x at p is going to be given by tan theta 1, yes or no? At q, this is the tangent at q. The slope of this tangent will give you the instantaneous rate of change of y with respect to x for the x that corresponds to q. Clear? That means now the slope of this tangent is theta 2. So in this case, whether the instantaneous rate of change from the figure for these 2 points P and Q, for example, out of visual inspection, can you tell me is dy dx more for P or more for Q? See, dy dx at P, instantaneous rate of change of y with respect to x at P is going to be tan theta 1, whereas instantaneous rate of change of y with respect to x at Q is going to be tan theta 2. So, which is greater, tan theta 2 or tan theta 1? Q, yeah, because see, theta 2 is larger than theta 1 in this case for the figure that I've shown, right? Theta 2 is larger than theta 1, so tan theta 2 would be larger than tan theta 2, and therefore dy dx at Q will be more than dy dx for x at, right? So, the steeper the tangent gets, the more is the rate of change of y with respect to x. Do you realize that? This was a gentler tangent, this was a steeper tangent. The steeper the merrier for the instantaneous rate of change, right? Higher the slope, the greater would be the value of dy dx. The slope of the tangent at P, the slope of the tangent at P is commonly referred to as the slope of the graph at P. Is commonly referred to as the slope of the graph or the slope of the function at P. Sometimes if I say slope of the graph at P, it would mean slope of the corresponding tangent at P. That is the implication. Clear? Are you messed up or are you fine? Okay. Now, although, you know, some of these things would be dealt with a little more technically down the line, but at least, you know, this treatment for a beginner, if you actually understand everything that I'm saying, it's good enough for a beginner, right? Now, this is a function and drawn between x equal to x1 and x equal to x2. Drawn between x equal to x1 and x equal to x2. So then, between P and Q, what's happening to y? Y is increasing as x is increasing. Do you realize that y is increasing as x is increasing? So we then say that y is monotonically increasing with x. We say that y is monotonically increasing with x. So we say that the function is monotonically increasing with x. Monotonically increasing with x in x1 to x2. In the interval x1 to x2, the function is monotonically growing. Function is monotonically growing. Function is growing means the value of y is growing with x. All right. Y equal to fx versus x. Suppose between P and Q, it's like this. X equal to x1 and x equal to x2. Now in this case, as x is increasing, the y's are increasing, the y's are decreasing. So do you realize that y is decreasing? Y is a decreasing function of x. Y is a decreasing function of x in the interval x1 to x2. So we then say that y is monotonically decreasing. We say that y is monotonically decreasing in the interval x1 to x2. Y is monotonically decreasing in the interval x1 to x2. Now, what is the difference algebraically between a function which is monotonically increasing in an interval in contrast to a function which is monotonically decreasing in the interval? Now, for a function which is monotonically increasing in an interval, which is this case, right? This is a function which is monotonically increasing in this interval. What we really have is, if at any point on this interval, if you draw a tangent, if at any point of this interval, if you draw a tangent, then the tangent makes an acute angle with the positive direction of the x-axis. Do you realize that? In an interval where a function is increasing, if you draw a tangent at any point, then the tangent makes an acute angle with the positive direction of the x-axis. Clear? In an interval in which the function is decreasing, if you take any point in this interval, if you took any point in this interval and you draw a tangent at that point, then realize that the tangent makes an obtuse angle with the positive direction of the x-axis, right? The tangent makes an obtuse angle with the positive direction of the x-axis. Clear? So theta is obtuse here. Theta is obtuse here for any x belonging to x1 to. Now, in this case, for a given x that belongs to x1 to x2, tan theta is greater than 0 because theta is obtuse. So for this case, since theta is acute, tan theta is greater than 0, theta is acute. That means, what is tan theta? dy dx at x. dy dx at x. Tan theta, slope of the tangent at any given x, is instantaneous rate of change of y with respect to x for that x. So dy dx is greater than 0. dy dx is greater than 0. That means, and this is true for any x belonging to x1 to x2. If you draw a tangent at any x belonging to x1 to x2, then the tangent will make an acute angle with the positive direction of the x-axis. Tan theta will be greater than 0 and therefore dy dx for any point in this interval will be greater than 0. Right? So in an interval in which a function is monotonically increasing, dy dx must be greater than 0 for any x belonging to that interval. Right? In contrast, examine this in which the function is monotonically decreasing. Theta is obtuse and therefore tan theta would be less than 0. For any x belonging to x1 to x2, tan theta would be less than 0. But what is tan theta? dy dx at x will be less than 0. And this is true for any x belonging to x1 to, right? That means, for a function which is monotonically decreasing in an interval, the dy dx at any point of that interval will be negative. Right? So, if a function exhibits a monotonically increasing character, then dy dx would be positive for all points in that interval. If a function is monotonically decreasing in an interval, then dy dx would be negative for all points of that interval. Does it sound all right? I mean, I'm sorry I have to give you this tablet in view of the larger interest, right? So please have some patience. Take it once and for all. Suppose there is a function like this. Right? This is x equal to x naught. Imagine an x to the left of x naught. The function, the dy dx is greater than 0 at this point. Why? Because the tangent makes an acute angle with the positive direction of the x-axis, right? So when x is less than x naught, which is written as x naught minus 0, x naught minus 0 means x is less than x naught. That's the symbolism, right? X naught minus 0 means x is less than x naught. That's what it means. So if you took a x less than x naught, then the slope of the tangent is positive. Why? Because the tangent, you realize, is making an acute angle with the positive direction of the x-axis. So what's dy dx at this point p? Greater than 0. And you can also see that if you're coming closer and closer to this point, the function is monotonically increasing. So dy dx must have been greater than 0, right? Whereas if you took a point Q to the right of x0, then realize that in this interval, the function is monotonically decreasing. So dy dx at any point will be less than 0, which you can see even geometrically because the tangent makes an obtuse angle with the positive direction of the x-axis. So at Q, dy dx is less than 0. So to the left of this point x0 call it r, to the left of this point x0, which corresponds to r, the function is monotonically increasing. To the right of r, the function is monotonically decreasing. To the left of r, therefore, dy dx is greater than 0. To the right of r, dy dx is less than 0. And at r, the tangent is parallel to the x-axis. The slope of this tangent is 0. dy dx at r, dy dx is 0. At r, dy dx is 0. That means the tangent is really gentle. The tangent is flat, parallel to the x-axis. Slope of the tangent is 0, and therefore dy dx at r must be dy dx at x equal to x of r will be 0. We refer to this point r as a stationary point. At r, this r is referred to as a stationary point. At this point, the function neither exhibits an increasing character nor a decreasing character because dy dx is neither greater than 0 or less than 0. It stays put, equal to 0. We refer to this point as a stationary point. Correct. So now obviously you know why I did all this. Say there is a particle moving in a straight line. There's a particle moving in a straight line, and its displacement is a function of time. Its displacement is a function of time. Displacement s of the particle moving in a straight line is a function of time. Its velocity will be a function of time. Let's say the velocity versus time graph that you draw, turns out to be the following. So this is the velocity versus time graph, right? Then at any time t, suppose on the Vt graph, this is the Vt graph, you draw a tangent. At any t. Then what would the slope of this tangent give me? dv dt, right? The slope of this tangent at any t would give me what? Rate of change of v with time. That's what we worked out, right? Slope of the tangent at t is actually ddt of v, rate of change of v with time. But rate of change of v with time is what? Acceleration. Now, which is an important fact to know, that if somebody gives you the velocity time graph, then to obtain the acceleration at any point, you draw the tangent to the Vt graph at that point. Slope of the tangent will give you the acceleration for that instant. Very clearly. This motion is characterized by a variable acceleration. Why? Because at different instants, the slope of the tangent is different and therefore a variable acceleration. Yes or no? Yes, right. So the slope of the Vt graph for a particle moving in a straight line at any point will give me the acceleration at that point, will give me the acceleration at that point. Clear? Now, if somebody gives you the displacement versus time, how displacement is varying with time. So somebody is giving you the displacement versus time. Then at any time t, if you draw the tangent at that corresponding point, then the slope of the tangent at t is rate of change of s with time. This is what we've learned. Slope of the tangent would be rate of change of this with this, right? Would be ds dt. Hey, but ds dt is the velocity. This is the velocity at an instant of time t. So if somebody gives you for a particle moving in a straight line, the displacement versus time characteristics, then to obtain the velocity at any point, all that you need to do is draw a tangent to the graph at that point. Slope of the tangent at that point will give you the velocity of the particle corresponding to that instant. Clear? Now, one fact which I cannot completely give to you, but I can just give you this result, that if I have y a function of x, in fact, why take y a function of x? Let's say, velocity a function of time. Let me take velocity a function of time between t1 and t2. This is how, let's say, velocity varies with time between t1 and t2 for a particle moving in a straight line. Then, again, without proof for the time being, let me say that the area under the velocity time graph will be the displacement. Area under the velocity time graph VT graph between T1 and T2 offers corresponding displacement the same interval. Area under the VT graph for a particle moving in a straight line between T1 and T2, instance T1 and T2, offers the corresponding displacement in the same interval. This is another fact. Again, I would refrain from offering a proof of this statement right now, but just take it from me for the time being, right? I know. Sad expressions on your face.